Selection, components, and communication. So we're going to look at more than Allen Bradley PLCs. I don't see my Siemens PLCs. Dang. We got a bunch of Siemens PLCs. I didn't think so. Identify important questions to determine which PLC device to purchase to distinguish between the Allen Bradley fixed and modular PLC. The 500 series, we got these. These are 504. And then we got the Micrologic 1000. We got the Micrologic 1100s. And then we got some Compact Logic 23, I think. I need to put one of those again. Select, and then we got the Siemens 1214. Select the module for this. Talk about chassis. We're going to talk about racks and different things on a modular PLC and what they're going to look at. Select the input-output module, and that's very, very important to understand that too. So we understand inputs and outputs. Why do we use inputs on a computer for? Okay, so I got my cell phone. How good would my cell phone if I could not input information into it to be processed? Okay, y'all understand that? So an input is where we input stuff into the PLC where it's processed, or into any computer. So any computer, if we don't have input ports, we don't have a computer. If I can't input information into my computer, there's no need to do that, right? You understand? And then we have output ports. This is where we bring information from inside the PLC that I, as a programmer, want to send out. Now, what you have to understand is all a computer does is run programs, right? You understand? And that's what y'all are going to be this semester. We're going to get into that. You're going to be a programmer. So you're going to have to learn a programming language. And of course, it's going to be what we call a high-level language because y'all don't want to learn the binary language of the processor, right? I don't know if anybody want to know that. I don't even know. I've tried to find out what processor Allen Bradley uses, but I haven't been able. I hadn't found that in documentation. I'm sure it's out there somewhere. Somebody could give it up. But we don't need to know that anyway because we're not going to program in the binary language of the computer. We're going to write it in a high-level language, and then we're going to compile it over into a machine language. So we're going to run an application on our computer that we call RS Logix 500. And it's going to allow us to do our programming. And then when we get ready to download it into the PLC, then it'll compile it over. Are we okay? So how do we input? How do we connect things up? We're going to look at that in, I don't know if that's in this chapter we'll talk about. We're going to learn how to connect different sensors to that. We got plenty of sensors. We teach a class called sensors in here. We'll pull out some of them and show them to you. But a sensor is basically the heart blood of automation. What a sensor does is indicates when things are where they're supposed to be, if they're not where they're supposed to be, if this occurs first or this occurs second. So if we didn't have sensors, then we would not have automation. Somebody would have to be out there doing what? Switching all this stuff, and a sensor is just it works exactly what humans, like the way human sensors work, is it takes a physical stimulus and converts it over to electrical signals so our PLC can control it. So we can process it with a program, just like our brain does. So PLC selection all depends on manufacturers, the servability, the flexibility, the expandability, the programming software. Is there any training available? And of course, there's any documents available. All these companies give just about all their documents away free about a certain PLC. So we've got tons of them out there about the different languages and the different instructions that we have that we could look up, and we'll be using those. And they're also out there. They should be out there on the website. How much training in PLCs have I had? None. Everything I've done, I picked up on mine. Alan Bradley, we're going to look at the 504. This is a modular PLC. Everybody understand on modular. So modular PLCs in the old days came with something that we call a rack. And this is what we call a 7-slot rack. You know, 1, 2, 3, 4, 5, 6, 7-slot rack. Okay, well, okay. And then in the back of it, we have what we call a backplane. And what's nice about these guys is that you figure out what you want. You know, if you want so many inputs, you buy a module that has that. If you want syncing inputs, you buy that module. If you want sourcing inputs, you buy that module. If you want syncing outputs, you buy that. See, I'm using terms that we're going to have to pick up because y'all don't understand that, but you need to understand that if you're going to get those modules, right? Everybody understand that? And then this in the back, can y'all see this? This is called a backplane. And all it does is we take these modules and we plug them into that backplane. And then of course we have to tell our programming application what we have. Because RSLogix 500 is an application that Alan Bradley or Rockwell just changed over here lately over to RSLogix 5000. So there's all types of PLCs out there that we program with that application. So one thing we got to do is, well, one of the first things we got to do when we start a program is tell it what we got, right? Understand that, and we'll show y'all how to do that. So one of the first things we'll have to specify is how many slots we have in the rack. We'll have to say we got 7 slots, and then we'll have to tell our application what we have in each slot except for slot 0. Slot 0 is always the CPU on the modular PLC. Okay, that makes sense. We call these slot numbers. So what you find out in computers, you gotta get used to starting with 0. Because this is an address. The analogy I like to use is, you know, you see football players all the time with the number 0 on them. It don't mean they don't exist. Right? So this is what we call an address. And 0 is a legal address. So when we start counting our slot numbers, we start with 0, 1, 2, 3, 4, 5, 6, and that would be the way the slot numbers go. Okay? So our first module that we would buy, we would determine what CPU we plug into that. Now this is a 500 series rack, so we would have to buy a version of the 500 series, right? Does that make sense? So like I said, this is a 504. This is the power supply right here. So a fixed PLC, which is what the 1100 is. So what advantage does a modular PLC have over a fixed PLC? You can expand it, right? You understand. What else? I bought my first. I use a desktop at home. Got a big screen on it. And I bought my first one that was put together. Up until then, I always bought parts and put my own computer together. Because if you buy parts and you put your own computer together, then you get what you want. You don't get what some manufacturer wants. So you get the video card you want, you get the sound card, the sound you want, you get everything that you want, right? You understand? Now, it's hard to get those type of things. It's hard to buy them. You can still get them online if you look around. These people make motherboards, and you can put your computer together yourself. And then, of course, if you put it together yourself, you get what you want, right? It is more expensive, but it's easier to troubleshoot. What we get now is we don't hardly get, we call them all-in-one computers. Even though they're big old computers, you got a big old screen, everything's still built inside a single chassis. And, of course, now if something breaks, well, maybe. Look at it. I can fix some. I can't fix notebooks. Notebooks you might throw away. Those things. Not unless you get somebody that's certified and they have the exact right tools to take those things apart. Tablets. It's hard to fix tablets yourself because if you don't have the right tools to get them apart, then that can be a problem. But this guy here, the initial investment for these would be more. But on that, if I lose an input or an output, I got to replace the PLC. Over here, I can do what? I can replace the module, right? You understand? So these are cheaper to maintain. Cheaper to maintain. It's just like a power. You see Alabama Power send 3-phase. They could build a 3-phase transformer, but a lot of times they'll use 3 transformers. Yeah, single phase, but they hook them up for 3-phase. Why do they do that? Well, it costs them more to invest in it, but it's what? It's cheaper to maintain. And over time, you go out and change. You have to change the 3-phase transformer out. So you save money over time. Those transformers always go. You ever see one blow up?
Especially the big ones.
So this is a fixed PLC. We could actually pass this without
Down.
Oh, ever down. So we can pass this around. Okay. This is a true fixed PLC. I got it. So a fixed PLC, you get what you buy, right? You understand that. A modular PLC, you can upgrade it, you can get what you want. Single housing fixed PLCs, the processor, power supply, and I/O module is usually all in one unit. And this is kind of different. So that 1000 has a power supply built in it. So we hook it up directly to Alabama Power. We bring a power cord into that thing, and it comes up instantly. The 1100 has an internal power supply. The Siemens, the 1200, doesn't have an internal power supply. So what that means is we have to get a power supply for that. So chassis, power supply, processor, and I/O module. Now we don't have very many I/O modules. And this is what we try to specify because we call them I/O, even though odds are they're either what? Input or output. Y'all understand that? A lot of our communication modules are true I/O modules. But we call these I/O devices, even though they're predominantly just input or output. So this module right here has 16. It's a 16-bit input module, and this right here is a 16-bit output. Y'all understand that term now, right? So this is the modular PLC. So you can get different communications. This comes with a data highway. It also comes with RS-485, which is if you ever seen a computer, so RS-242 is the same thing. It's just and that's the only two here. But if I wanted to have Ethernet IP or Ethernet, then what could I do on this? I could buy a communication module. No, I could probably buy a communication module and go ahead and do that. So even for most PLCs, we can buy different. It comes with communication built into it, of course, because we have to have some means to hook our computer up to it, right, and program it. But then most of them give you the ability to go to other modules. Some of the other communication standards that's out there, like Profibus and DeviceNet, and Ethernet IP, and Fieldbus, and there's a lot of them out there. So the power supply on the rack mount is going to occupy, usually everyone I've ever seen, the power supply in the first on the left, but it doesn't occupy a slot. It doesn't have an address. So power, right? That makes sense. This is the predominant power. Power PLCs have been around a long time. So you can get them that runs off of 240 volts. I've never seen one that runs off 440, but you can get them that powers up off 240 AC. You can get them that powers up off 120 volts AC. You can get them powered up. I've never, and 24 volts DC. And the book talks about 120 volts DC, but I've never seen that. But it don't mean they exist, right? So 4 slot, and they're talking about the 500 series. So we can buy these 4 slots, 7 slots, 10 slots, and 13 slots. If you buy the 4 slot though, you're only going to get 3 for your I/O modules, right? You understand that? Why? CPU. Yeah, the CPU occupies 1 slot. CPU always occupies slot 0. A number of slots can be expanded to a maximum of 30 by interconnecting up to 3 chassis. So what we can do, there's a little slot here on the side. You can pop that off, and then we can plug in a cable and run it down to just a plain rack. And it won't have the power supply on it because it'll power up through the backbone. I don't know if that's it or not. That would be a chance. When installing the PLC components in the chassis, the processor must be selected in slot 1. 0. Input and output modules can be in any other slot. Slot 0 in the modular PLC is reserved for the processor. Now, fixed PLC, the processor has no slot, right? You understand that? Because it's where the processor is actually part of the unit. A complete, say, power supply, processor, and then modules. They say I/O modules, but literally you can buy all type of modules that go out there besides for I/O. Okay? An I/O module is referred to as, I don't know about that. What did you say that? Actually, when we address this stuff, this is going to be the first module is going to be addressed. We're going to have to figure out how we can tell our program which one of these to select. Make sense? So I don't know where this came from, guys. So this would be slot 1, and this would be slot 2, and that's part of your address. So the way now there's a little more to it. But if I was writing a program and I wanted to address that slot, and I would start off with I, what do you think I means? Yeah, good. And then the way Allen Bradley works is we'd put a colon, and then we would specify a slot number. So that would be slot number 1, and then I would specify a bit. That makes sense? Okay? So when I did this, now there's more to it because we can get 32-bit modules, and we'll have to talk about that later. But so and then I would look over here, I'd say 0, 1, 2, 3, and that would be the input that I would be at. So whatever I hooked up to the module on input 3, then that would we just address that. Makes sense? Now output, I can think out. Siemens changed this. Siemens would uses O. I'm sorry. Allen Bradley uses O, and then we put a colon. And what slot is our output in? 2. And then if I said /5, then what we would have just done is we would have told our application that we were going to address 0, 1, 2, 3, 4, 5 output. That makes sense? So we start off, when we put these addresses in, and this is true in every PLC that I've ever worked with. So what you need to know is know the numbers of the wire, of the slots. I'm not going to show you Siemens, you'll get confused right now. But I do like Siemens. Allen Bradley uses O, so it gets people confused because they'll hit the 0 key a lot. And then, of course, you'll get a syntax error. What Siemens decided to use for outputs, they use Q when you address the outputs on there. So you can't get a Q confused with an O, right? So I don't know what they're talking about referred to as module 0. That's not correct. I need to look at that. So IO ports are voltage and current rating. So this is also true, especially on your output ports. Your output ports are not designed to drive high power loads. In fact, usually rule of thumb, if you don't know, but you need to look it up, and you can look up the data sheet on your PLC on that output module, and it would tell you how much electrical current it could drive. Rule of thumb is about 2 amps. But some of them can drive more, some of them can do what? Drive less. So you're not going to run a big motor on a PLC. But what you can do is you can pick up a relay, and then the relay can do whatever you want to. Everybody okay? So one of the things you're going to be rating is what voltage we have. So we can get AC output modules, and then if it's an AC output module, we're going to have to figure out, what voltage you're going to need out of that thing, right? Understand that. We can buy DC output modules. That's where seeking the source comes into play, which we'll talk about. Okay? So if I look at these are DC modules. It says this is an input, and it says DC sync, and this is an output, and it says it's DC source. So I'll have to figure out what that means. Anybody know what that means? Power supply provides power to the chassis, the backplane, and that's the processor module. So okay, so this is the chassis, right? Understand? I'm sorry, this is the rack, or it's also called the chassis, but I think the book calls it the rack. And this down here that's got all these plugs in it, this is the backplane. So this power supply right here, which has a regular power plug on it, we plug 100. When we usually use the term power supply, they're actually DC power supply. Electronics does not work off of AC. Anytime you're going to have electronics, you got to have a power supply, right? So that's what this guy does. It converts it from AC over to what DC is designed to run the process, the electronics. And then all the modules run off that same power. And usually in PLCs it's 24 volts, plus 24 volts. Now it don't mean you can't switch 120 volts. It's just that the electronics runs off what? 24 volts. So here's some Allen Bradley 500s. We got the 504, this is their part number. We got a 504. It's actually a 5/04. So we just call it a 504. And this comes with this much rounding. Yeah, but you got to understand, this is all binary codes. We don't have to do any graphics, right? So what requires so much memory is this graphical world that we live in. So now your computers, you can play all these games on them, right? And the graphics is just unbelievable that we've got available to us. That's what eats up processing power right there, is the graphics that we play around. How much information you got to move between our application and just the video. We're using mine lower than what it wants to set it, but we can see. So we can go. So I'm using 1024 by 768. So that means I've got 1024 by 768 picture elements up on the screen. And odds are I'm using 32-bit color. 32-bit color means I can do 32-bit color means I can do 32,768 different colors. You understand that? And that's 6 bytes of memory for every pixel up on the screen. So this would be how much video memory is up there that I've got to update every time my screen changes. That's a lot of memory, right? You all understand that? People out there running 64-bit memory, 64-bit memory. You know, that's 8 bytes, guys. That's 8 bytes of memory. 8 bytes for every pixel. How many colors would that be? More colors than you can discern. So this is where we require processing power. A PLC does not do graphics. It does not run a graphics display. Well, a lot of your new PLCs can actually run a web server, which is pretty neat. Which means you can download web pages. But that's y'all understand web pages are still text, right? You understand that? We use a language called HTML, hypertext markup language. So even a web page is nothing but text. So since it only deals with codes and don't deal with all its graphics and have these graphics processors, then we don't need a lot of memory inside these machines. In fact, when the IBM PC first came out, when the IBM PC first came out, the maximum memory you could put in it was 640K. But everything was what? Everything was text. Everything was text. So discrete I/O modules. These are digital. So anytime the book uses the term discrete, they're talking about digital input modules. So what we need by digital input modules is they're only going to look for 2 states. Yeah, but it's going to be a voltage, right? You understand? And so it all depends on what you're dealing with. If you're dealing with 26 volts AC, then 26 volts from a sensor would be considered a 1, and 0 volts would be considered a digital 0, right? If you're dealing with 24 volts, then 24 volts would be considered a digital 1, and 0 volts would be considered a digital 0. So what's nice about a digital is that it only requires 1 bit of memory. Now, Alan Bradley goes in words. So how many bits in a word? No.
Wait, no, that's 16.
Oh, guys, this makes me feel bad. No, that's a double word. So that's some terms you're going to have to learn. You're going to have to learn those terms. Yeah, it takes 5 weeks. So we got bits, we got nibbles, we got bytes, we got words, we got double words or long words. We got slide words or double long words.
So 16.
16.
And then 8 is big. 5. 4 is.
So Alan Bradley, what we do is when we got a 16-bit input module, then that would take 1 word of memory. And every bit inside that address would represent what goes on to that module. We can actually see this, guys. We'll show you some stuff. Analog. So I could buy an analog module. We didn't have them. The 1100 has analog inputs on it. The 1200 that we have, 1214C, has analog inputs. It's got 2 analog inputs on it. And then we bought an analog output for that. What's analog? What's the difference between digital and what's analog?
Analog.
Very constantly changes. You know we live in an analog world, guys. You know understand that. So we need a method where if I want to measure temperature, and temperature is very important in the industry. We measure that all the time, and I want to control that with my PLC. So we're going to have to input analog, and then what do we have? We have something called an analog to digital converter. That converts it over to a binary number that reproduces it. Specialty modules. So we can get current loop modules. We can get, I said, like Ethernet modules. We can get all these different modules besides IO modules. But when you try to program them, you got to tell the application exactly what you got out there, right? You understand? Because, like I said, RS Logic 500 it's capable of programming all of Allen Bradley PLCs all the way up to their compact logic line. So you got to be able to say, okay, I've got this CPU, right? You understand? I've got this type of module, and that kind of stuff. So if you get on one of the modular PLCs, then you're going to have to. We'll show y'all where you find the number on the module. So it's got a number on the door. And what you do is you look up that module when you set up a new program. So we show how to configure them. Fixed PLCs are a lot easier to configure because they're what? They're fixed. So usually when you load up a fixed PLC, all you do is tell Allen Bradley, I've got this PLC, and then it knows what inputs it's got and outputs. Each input and output module has several ports or terminals. For example, input modules input module 1 may have 16 ports, and output module might have 8. The more portals you have on that card, the more expensive they're going to be, right? I think Allen Bradley makes up to 16-bit input modules and output modules. I'm sorry, 32. Ports and modules specifies when they are specifically used in a ladder diagram addressed by the module and port number. And we already looked at that, right? Everybody okay? So this is RS Logic 500. And if I was going to come up here and set up a new file, a new program, look at the first thing it wants to know. It wants to know what process that is. Right, you understand? Because it's got to be able to compile my program over to all the different processes. So the first thing it wants to know is what processes you have. Right? You understand that? So I would come over here and I would have to look at the door on this one. It's pretty neat. We come over here to the top and open the door. Down at the bottom, it gives us all that information. Because what you have to do is you have to select it by this part number. When I get down to these fixed PLCs, like the MicroLogic PLCs, since they're all fixed, then we can just come up here and choose a MicroLogic. So we have a MicroLogic 1100. I'm not going to use that. So this is MicroLogic 1000. And this is what we have. Okay, so far. This is where I would have to go in and configure the IO racks right here. Of course, this guy. So if I was on the 504, then what I would have to do is I'd have to figure out which 504. Well, let's just choose one because we're not really doing anything. So we got a 504. I think we got a C. I think doesn't make any difference. And then what I would have to do now is I would have to come up here and I'm going to double click. Y'all see IO configuration over there? I'm going to click on that and it's going to say how many slots do we have in our rack. So how many slots do we have? 7. And then over here on the right hand side, these are all the modules that thing supports. So the 504, these are all the modules that the 504 supports. So I'd have to come in and figure out which input module we're going to have, which output module we're going to have, and then I would come up here and I'm telling it, notice what's over here. This tells me what slot is installed. And you don't have to install them in consecutive slots. We could drop down to like 4 if we wanted to. I don't know why we don't do that. But you would have to specify which slot you have that I/O module. And then once you do that, then you're ready to write the program. Of course, we'll probably get errors because I probably got the wrong CPU. So that's a 16-bit fast sync. I don't think ours is a fast sync. Then we have our output modules, analog modules. Ours is not triac output. Ours is DC output, 24 volts DC. That's not good. And then once I have this set up, then we should be able to start writing our program. So what we would do is, this is a of course it says I got an error. So once I pull down this device, this is one of our input instructions. And then the first thing I would have to do is enter what? An address. So I'd say N:1/0. And then we'll talk about this later on. Makes sense? So this is where this address comes into play. So what I just did is tell my program the address was slot 1, input 0. Okay? So the inputs go from 0 to 15. And we'll get familiar with all this stuff over here too. This is called the project tree over here. And this is also common to Siemens PLCs too. It's on the left just like this is. Guys, if you learn how to do RS Logic 500, Siemens is a snap. So specify used in the ladder diagram address by the module and port. Okay? So one thing we're going to have to understand is that, for one thing, we have an input module. And when you draw your diagrams, you're going to have two. We got the symbols that we use inside our PLC, inside our program. And then we have the symbols that we use for electrical motors, for electrical control. When you draw the diagram on how you hook up your PLC, you're supposed to use these symbols right here. Everybody understand that? So what's some of the symbols? I've never seen that symbol for a motor. No. So these are symbols for what? Right. So I would come up here and I would hook it up to one of my outputs. I don't know what this is up here. But I would come over and hook this up to one of my outputs. And we'll just do this kind of off the wall right now. So I'd hook this up to one of my output ports. And then I would, when I draw it as that symbol. That makes sense? Now, let's say it's DC, and this guy puts out a plus. Then over here, I would have to have my minus, right? Everybody okay? Huh?
Can't switch DC polarity.
Well, you can. This is what we call a sourcing output. Now, once you set it up, you can't. But sometimes it's up to you to decide whether your output module outputs a minus or whether it outputs a plus. This one we have no choice. This is called a sourcing module. When it says sourcing, that means it outputs a plus or DC. If it outputs a plus, then I got to provide the what? The negative. Right? You understand? So sourcing means plus. What do you think sinking means? So I would come over here and so output 2, I might come over here and hook up a motor or a relay. Let's do it that way. And then I have to provide this, right? You understand that? So we'll have to run that out. And I didn't bring my IO modules over here to show you how that works, but I'll try to remember to bring those. And we would call, this guy would be sourcing. So if the PLC provides the plus, it's called sourcing. If the PLC provides the minus, it's called what? Sinking. And that came from digital, guys. So this PLC says the inputs are sinking. So what I would do, that means it puts out a what? A minus. And I might come over here and hook up a push button. And then what would I have to provide? This would be a plus. So sinking inputs, that's what the PLC provides, and you have to provide the other one, right? You understand that? So if it's sinking, the PLC provides the minus, and then you would have to provide the plus. So these are all sinking inputs. So I would come over here and I'd run this wire, I'd just jump it over, and then I could come over here and I can hook up all type of input devices to this. But what you got to do, guys, is you got to know the symbol. They've cut off a temperature switch, which so I have a push button hooked up to input 0. I have a limit switch hooked up to input 1. I have a thermal switch hooked up to input 3. I skipped over input 2. So we're going to have to start working on all these symbols, because you're going to have to almost every lab you do, you're going to have to wire up how you hook up your inputs. Now, we're not going to be using the limit switches. Anybody going to show you this? I'll show y'all limit switches and temperature switches and pressure switches and flow switches. But all they are switches, right? So a manual switch, you have to come up here and do this. Well, if I can do this, then a sensor can do this, right? You understand that? The sensor can provide me a 1 when the level gets up to a certain height, or it can provide me a 1 when the temperature gets up to a certain height, or it can give me when it gets so low, right? You understand? So all we're going to do is just simulate these with these switches. And when you get out in the industry, you're probably not going to see a PLC use any switches. They use selector switches, but they usually don't use these little toggle switches. We use a lot of push buttons, and I'll show you some of those. So this is what they're showing. Here they're saying common, but what you have to understand, sometimes the common is selectable. Right? Does that make sense? So sometimes the common is selectable, and on DC now AC technically does not have a polarity. So this plus and minus and this sinking and sourcing only comes into play if you have DC inputs and DC output modules. And DC input is very, very, very popular, and 24 volts is very, very, very popular. And why? Because 24 volts is below what NEC calls the lethal voltage. NEC, not NEC, the NAFTA 70E standard. If y'all hadn't heard about that, if you get in the industry, I guarantee you will. It's a safety standard, and what they say is anything above 50 volts is considered to be lethal. It don't mean you can't get killed under 50 volts. It's just highly unlikely, right? You understand? It's just like I tell people, you might follow all the traffic rules. You might stop at all your stop signs. You might not ever run a red light, but it doesn't mean you're not going to have a wreck, right? You understand that? But if you never stop at stop signs and you never stop at red lights, right? You understand, and you text all the time, then you are going to have a wreck. So that's what we're saying. So what they're saying, anything below 50 volts, it's highly unlikely that that's going to hurt you. I mean, it would have to catch you in extenuating circumstances by taking the 24 volts and putting it up here on your ears. Or if you got big cuts on your finger, and you sand your finger, you sand your fingerprints off. 24 volts will probably get you. So what we're going to do is we'll have to provide a common, and we'll show y'all. We're not going to wire up the PLCs in this class, but you're going to draw the way you would wire them up. If you take the PLC 3 class, that's where you actually wire up the PLC. And it's a good class, guys. It went real great. So this makes sense? Now normally we don't run motors off the PLC. No, unless they're little old tiny motors, maybe a fan motor, something like that. What we normally do is we'll come over here and we'll have a relay. And I've showed y'all relays, right? What's the advantage of a relay? What can we do with a relay? Now we can take a low voltage to control a what? High voltage or even high currents. So a lot of times we'll use that. We might could run a bell. So the ports are typically rated at low amps, right? As I said, typically around 2 amps, but you need to look up the data sheet on the module that tells you what it runs. Ordinarily connected to 14 gauge wire. 14 gauge wire has more than a sufficient amperage rating for carrying current from IO devices in the board. 14 gauge wire is it's rated, NEC rates it at 15 amps. It can run like 30 amps, but NEC rates it at 15. I don't know what NEC is, right? Yeah. I've never seen 14 gauge wire used. That's pretty big wire. In most applications, output devices require large currents and large voltage ratings. A magnetic relay should be used to connect large voltage and current equivalent to the output device. So what we do is we use the output port to energize the relay, and then we use the contacts on the relay to run the bus. So we're going to see a lot of relays. Sourcing and syncing. So this is what we're talking about. So sourcing and syncing depends on the PLC, what your company uses, what they prefer, what type of sensors they buy. So when you buy a sensor, one of the things, when you buy a DC sensor, one of the things you got to specify is if the sinker is a syncing sensor or is a sourcing sensor. Now, if I've got a syncing input, I better buy a sourcing sensor, right? Because sourcing means it supplies the plus. Syncing means it supplies the what? Minus. I understand that. By the way, they very seldom call them syncing and sourcing sensors. And we're not going to explain this. I'm going to just give it to you. Take it for granted. An NPN sensor is a syncing sensor. A PNP sensor is a sourcing sensor. If you take solid state children, we talk a little bit about it in advanced PLCs. So what we're saying is if I come over here and I have this PLC, and if my PLC is sourcing, right, you understand, then my what? sourcing, this occurs when the current flows out of the PLC. So here they're saying what? So this is an input. Current's flowing out. So it means my device needs to be what? I like to explain it a little better than that. I mean, they try to make it complicated. It's just, if you're using a syncing input, so this would be a sourcing input, then what it does is it provides the plus, which means you have to provide the what? You have to provide the minus, and that's what they're doing over here. And what you would do is you would have your DC power supply, and so the plus would hook up, and then you would come over here, and then you would have this would run all the way down the line. So this would be your common. A lot of people think common is ground, but it's not. In PLCs, you need to get away from that. Common is exactly what it's supposed to be. It's a thing that multiple devices connect to, right? So we can have a positive common, or we can have a what? A negative common. So we would run a wire out of our power supply. So we'd hook the power supply up to the module. Now, on a modular PLC, you don't have to do this. On a fixed PLC, or these PLCs that I call hybrid PLCs, you have to hook it up. You have to take a DC power supply. Now, a lot of these guys have an internal power supply, DC power supply, but they're not, most of them are not high current devices, so sometimes you have to use an external power. And I'll show you all that too. Now, like I said, we don't have to worry about this. We don't have to worry about the power supply, right? Y'all understand that? But what I have to do is if it's a syncing input, and I got to come over here and get the minus, I got to get the plus and run it to all these terminals. Because I have to supply the what? I have to supply, if the module supplies the negative, then I've got to run the plus to everything. Right? If my module supplies the positive, then I've got to supply the negative. So this is a syncing input. So I could go to every one of these switches and we'd find there's a wire running from, this is a syncing input. I would find there's a wire running from the plus. I'm not sure if we're close to. Yeah, this is the DC. I've got a wire running from the plus to every one of these switches. This is a sourcing output. So it's going to provide the plus, right? You understand? So I have to run the minus to all my output devices. Okay? Don't understand why we had that little lecture on DC and AC and that kind of stuff. So that's syncing and sourcing. So literally sometimes we get to choose, sometimes it's fixed. So I can buy a sourcing output, I can buy a sourcing input module, or I could buy syncing. Over here in the US, we like to use syncing inputs and sourcing outputs if we use DC. If they're AC, it don't make any difference, right? What you need to do is run your neutral wire out in both instances. Are we okay? Everybody okay? Yes, no? So this is syncing. So I've got my negative connected to the common on my module, and then my plus goes to all my devices. The 1100 that's over here, you have the ability to decide whether you want your inputs to be syncing or not. And let me borrow my camera a little bit. I'll take a 10-minute break. So this is the 1100. And these are the inputs right here. So this guy doesn't have a rack. So the CPU does not occupy a slot. So that means all the IOs start with 0. That makes sense? So if I wanted to address this guy right here, this would be input 0/0. This would be 1. But if we notice right here, can y'all see what that says? DC common. And that says DC common. So I can, if I hook up a minus to this DC common, then these guys would be syncing. But I could hook up a plus to these, and these guys would be sourcing. So this is one situation where you decide whether you are syncing or sourcing. Alan Bradley's good at that. Well, they let you decide. If I just hook a minus to both of them, which you can see I got a jumper right here. So here's my minus coming in right here on this orange wire. I'm sorry. Here's my minus coming in on this blue wire. And what I do is I just jump them together. So I'm putting minus, so I've got mine set up. I got my input set up to sync. Are we okay? That makes sense. Now this guy uses relay outputs. Now what's nice about relay outputs is up to you what you want them to do. You can hook them up for DC, you can hook them up for AC. You can hook them up for AC, and what you do is down this common line right here, you just put your neutral out there. But what's nice about relay outputs is you decide whether you want DC output, you decide if you want AC output. You decide if you want them to sync, or you decide if they're the source. So you notice what we have on every output. I don't know if y'all can see this, but every output, we have a DC. It says AC or DC right there. So that's one advantage of having a relay output is that you decide what your common's going to be, right? You understand if you're using DC, you can decide whether you want to sync, or you can decide whether you want to source, right? That makes sense. You can decide if you're going to use AC. If we use AC, there's no such thing as syncing and sourcing because AC has no polarity. Y'all understand that? So what you would do is you'd bring your neutral and you would jump it down through all these commons. And y'all might not can see this, but here's all my little jumps right here. Can y'all see it? So here comes my power supply right here. So this is my plus, so I have it hooked up for sourcing. And then I have it hooked up to the common of all those outputs. So on mine, I have the outputs hooked up for sourcing, and I have my inputs hooked up for syncing. Okay? Now, why do we do that? Well, all these switches are sourcing switches. So if my switches are sourcing, then by George, I better set up my PLC input to be what? Syncing. And all these output ports right here, these are syncing. So I'm sorry, these are sourcing. So syncing inputs, these are sourcing, these are sourcing outputs. That makes sense? Or did I tie that up? Now these are the trainers we're going to try to eventually go to, because we can put any PLC we want to on them just about. So everybody okay on syncing and sourcing? Yes, no? Jacob, you said you was okay, right? User memory holds the ladder dot like about 75% of total memory. So the CPU uses very little memory. System memory stores information needed to execute the user program, right? And we'll look at that, how it's divided up, and we can see that when we bring up RS Logics, usually they divide that memory up. Input status holds the status of the discrete inputs. Output status holds the status of the discrete outputs. timer status. No, I might not be able to do this because it'll take a while. Where's the 1000 at? This uses Ethernet, so I have to set up an IP address on it. Where's 1100 at? 1000. The suitcase. So this guy's got it's got its own power supply in it. So we're gonna plug this into Alabama Power. And then we have to have a communication cable that we communicate. Oh, in fact, it's right there. We have to have the communication cable that we use to connect to the PLC. This is a RS-485 or RS-232 port. Our computers don't support that port anymore. There's a lot of ports that it don't support anymore. So we get these things, they're called, we call them dongles. But what's the main port as far as I'm concerned? USB, right? USB, Universal Serial Bus. So we buy these dongles, and what this does, it takes the USB and converts it over to RS-232 or RS-480 or 485. So I'm going to plug this into one of my serial ports. Plug it into my PLC. And this is kind of off the cuff, guys. I hope it goes right. Then what we'll do is we'll bring up an application where we establish the communication with the PLC and my computer. Alan Bradley calls it RS Links. And then we're going to go to communication, and I'm going to configure my driver. And this is our driver right here, and it's running. Okay, does that make sense? I'm going to configure it, and what it's going to try to do is it's going to try to find my PLC. Okay, so it automatically found it. It's hooked on an old serial port called COM, and we'll talk about that at the end of this chapter. It's communicating at a baud rate of 9600, one stop bit, 4 duplex. And we're configured it, guys, and we're connected to that PLC. So I'm going to say, okay, I'm going to come up and bring up my actually programming software. So the first thing you're going to have to do is get your computer to communicate with your PLC, right, with the interface that you have. So what we're going to do is we're going to go to a new program. And we're not going to save this one. This is nice. It's a fixed PLC, so I'm just going to find the MicroLogic 1000. Okay, here it is. Oops, which one is it, Rich? This is one. Okay. Now I'm going to go to comms and see if it's out there. Who's active online. And there he is right there. Okay. So what we have over here on the left-hand side on what we call the project tree. So this is the same setup whether I was communicating, if I was, of course my computer, if I was going to the 1200 over there, 1214 over there, the first thing I got to do is what? Set up the communication link. Yeah. That's not good. Okay. We'll see. I might have chosen the wrong PLC. But once I do that, in Valley I did. There was 3 models. I needed to figure out which one it is. Huh? Yeah, but it's the wrong model of the 1100. I don't have the. This is a 1761L. That's what I should have done. So I've got a MicroLogic 1000. I got a 761/L-6 DWA. And I don't see it, but this is the one we chose, right? So, no, it's not analog. Looks like it's still going to have it. But what we have over here on the left-hand side is these registers right here. So this, see, you'll see the status right here. So this is memory that's still failed. This is the memory that we have that actually runs the processor. And here's our input status, and here's our output status. I'm gonna come over and bring this up. And what this is a word that holds the input port. And of course, this is showing me what's going on with input 0. This is showing me what's going on with input 1, 2, 3, 4, 5, all the way up to how many inputs this guy here has. This guy here has, it's got 9 inputs. So this is the memory this is the memory inside the PLC that keeps up with the status of these things. Now, if I could switch it into run, if I could get it to work, then there's a program. There's a program. So if I was to have this running, if I could get it running, when I press that button right there, if that was the 0, that right there would go to a 1. When I press the next button, it'd go to what? You know, when I released it, it would go back to a 0. So this is the data table that keeps up with the status of the watt, the inputs. This is the data tables that keeps up with the status of the outputs. This guy's got, now you gotta be careful. They're running this guy on 120 volts down here, so don't touch him. So y'all need to keep the little door closed, right? So this has got 1, 2, 3, 4. This has got 6 outputs. And that's what you got. So what if I need 8 outputs? Yeah, you're screwed, right? You didn't buy the right number of fixed PLCs. If I run out of inputs or outputs on that guy, what can I do? I can add another module, right? You understand that? Now, I think I told you the technique they're using now is to get away from the chassis. And what we do is we actually bring the backplane through the PLC itself. So if we come up here, look at the 1100, it's got a And I'll try to figure out why this ain't running, because it seems like, let's kill this guy, let's stop this guy. That concerns me. It figured okay, right? I'm sure it's this guy right here. Yeah, this is my, oh, I know what's going on. This is the guy we should be looking at. There it is. There we go. So this is Ethernet IP. That's what I was doing. So this is Ethernet IP. This is the address, the IP address that would be assigned to 1100. We're doing the DFI or the H or the 485. Yeah, doing something. This is the actual program that's in the PLC right now. By the way, it's backwards on PLC because the PLC considers itself to be a computer, and that's a computer. It considers it to be the main guy. So what we do is normally when you download stuff from the internet, it comes from the internet to your house. Right? But when we put a program into the PLC, it's called download because it considers it to be the main guy. This is your sending information. So if I want to get a program from the PLC, I upload. If I want to send a program to the PLC, I download. But this is the technique they're using now on these PLCs. So we are getting away from the rack. And what we're going to is we're sending the so this is called a DIN rail, guys. It don't really stand for anything. And this is a standard mounting system that we're using a lot in controls. And you'll see this big slot in the side. Well, I can break this open. I'm not going to do it. And then that's going to be the expansion bus right there. So I buy the module and I just slide it onto the DIN rail and snap it into the backplane. So we're getting away from the chassis. And I call them hybrid PLCs because they come with a set number of inputs and outputs in the PLC itself. And then if you need to update, what you can do, you can add more modules. So this is the program that's actually in the PLC, which is pretty neat. Okay. And what we can do with the PLC is, this is software, guys. So all this is a program, but we're addressing one of our inputs. Which input am I addressing? 0. And I'm addressing one of my outputs. I'm output 0. So what we can do is we can go online. And what it shows us, and we'll talk about this. So we have what we call power rail. There's really no power. It's all logic, right? Understand that. So we make our circuits between the one on the left, which technically we call L1, and then this over here is L2. The green indicates there's what? It's power. We're actually monitoring what's going on. So I'm going to come over here and I'm going to press my input. And what it tells me is it tells me it's true. And we have this hooked up to a light, by the way. So my output is actually hooked up to a light. So this tells me, the green tells me that that input is true, right? You understand? And it tells me my output is true. And we have that light hooked up to the output port. So this is hooked up to an input port, right? You understand? Now if I come over here and look at my status of my inputs, and this is what they were showing. So here's my inputs. I'm going to press that button right there. Can y'all see what it went to? 1. Now it's a what? 0. If I go down the next line, it don't make any difference. There's nothing hooked up to it. So this is what we're doing. We're taking an input and we're converting it over to a digital quantity. So see, that's a 1. Here's this one. This is a what? 1. Now I'm doing. Now 5 is on a switch. It's on a selector switch. So here's these switches over here. So that's all you're doing when the PLC program reads that input, it stores it in this. Yeah. So if I come over here right now and I looked at my output status, is what they was talking about. So that would be right here. Then nothing's going on. But if I come over and press this button, it went to a what? 1. And notice it's in a word, 16 bits. Okay? So that's what the PowerPoint's talking about. So these inputs are actually connected up to this thing. So we could come up and make a neat little circuit. So by the way, you can't program them when you're online, right? So I could come up here and switch this thing offline. And no, I don't say that. We'll create it. So let's come up here and do something like this. So I'm putting one we're called a normally closed, right? And this right here is a down drop. I'll come over and slide this in here. And I'm gonna put another contact right here. And I'm gonna call it now. It says I had an error. Cause why is it an error? Cause I don't have these, I haven't given these things addresses, right? So I'm gonna hook this up to input, colon, 0, colon, Rich, colon, 0/1. That'd be the next switch, right? And we'll talk about symbols here. We're going to require y'all to do symbols. But we'll just leave that blank right now. And then on that right here, I'm going to assign this contact to that output relay over there. Which is it's not a relay, but it's a symbol of a relay, right? So output 0:0. It still says I have an error, so I'm going to go back and make sure I got the right syntax. I'm going to hit this, and it came back clear. So what can I do now? Go up and download it into my PLC. We'll call it untitled right now. This is where you would, it says is in remote run, so we need to switch it out. So it switched it out of run, so it we'll go back online. So what we have here is we have a basic, what we call a memory circuit or sealing circuit. And I'm going to come over and press switch 1. And I let go of it, and what did it do? Let's see the way it sealed itself in. And how do I stop it? It should be able to hit the second button. And that's our first program.
Now, we could go over here and wire this up. I believe we could wire it up. We got everything we need back there to wire it up. But we really don't have to do anything now. Now, we would still have to wire the input and we would have to wire the outputs, right? You understand that? And we're not getting into our wiring. Like I said, y'all draw on this semester. But there's your output table. That's what they was talking about, the output table. So you can actually monitor us. And we'll talk about forcing later on. So we're talking about the memory uses, RS Logic 500 assigns memory to different types of data. Most of your newer PLCs, you assign the memory to what type of data you put in. Okay? So we ladder input status, output status. We'll talk about timers. We'll talk about counters. Are you okay? And that's as far as we'll go in here. In advanced PLCs, we'll look at math. We'll look at logic. We'll look at shifting data. We'll look at sequencers. We'll look at the high-level instructions. So as far as we're going to go this time is counters. But y'all should understand, what does a counter do? Counts the number. So if I had a counter, if I come up and hit this 5 times, it would count 1. 5, yeah. Depends on, it could be a down counter. So we have up counters and down counters. A timer, what does a timer do? Y'all see timers all the time. They time. They give you they say true or false for a certain amount of time, depending on what you want to do. Printers, some PLCs run printers, but they don't usually do that anymore because normally we hook them up to a what? To a computer. I haven't seen a PLC that would run a printer from the PLC itself. I haven't seen one of those in a long time. We do have them that will run what we call HMI panels, human machine interface panels. And those are the predominant method used. You still use push buttons and you still have all these sensors out there, but we're in a graphical world, right? And I'll try to bring an HMI panel, or hopefully we're going to get time and go over to the manufacturing lines over there. And then of course, some of them used to run dedicated programming devices. Now we don't use dedicated programming devices. We use a what? A computer, and we install an application on it. Right? You understand? So we have an application we install on it that allows it to program in a high-level language like ladder, right? You understand? And then it has the compiler in there that compiles it over for us right into machine language. So these are the different ways we can communicate. The data highway 485, which some people call it IEEE 485. If you've been around for computers a long time, that's the ORS 232 interface. Then we have Ethernet. This computer right here doesn't support Ethernet. The Micrologic 1100 supports Ethernet. And then that's about the Siemens PLC, that's about it. That comes on the PLC. Now, if you wanted to use the data highway or DeviceNet or Profibus or those, and you would buy a communication module, right? Just stick it on there. But your PLC is going to come with at least one mode of you communicating with it and your programming device, right? You understand that? This guy right here has been around for years. Even the brand new Allen Bradley PLC still supports this 485 interface right here. But now most of their PLCs have an Ethernet interface on it too. But Ethernet is a little more complicated, and I'll show y'all that on the 1100s. And so DF, the ORS 232 interface with 7 anything, y'all. Full duplex and half duplex, you need to understand that. Anybody touched on ham radio or what was the cell phone that Obama liked to use? BlackBerry. BlackBerry was originally half duplex. People would use that all the time. But half duplex, you communicate in two directions, but not at the same time. So it's like those CD radios are still out there. Next to it, yeah. It's one you can. It was so funny. When I was over in Japan, we had to go through a bunch of ham radio licenses, but we talked on the phone. And every time you get through talking, you'd have to say over, over. And listen to one guy over here talk to his wife. He says, "I love you, over." Full duplex. That's what our cell phones use. Full duplex is what? Two directions at the same time. We have simplex, which we don't run into. Broadcast TV uses simplex. What's simplex? One direction, right? And then half duplex. Ham radio uses it. 2 meter uses it. CB uses it. The old Blackberries used to use it, right? And this is still pretty popular. But full duplex, USB is half duplex. Now, anytime you see 2 wires, it's half duplex. To do serial full duplex, you got to have 4, right? You understand that? So yeah, Ethernet depends on what version you're running. If you're running down below like 100 megahertz, it's probably half duplex. If you're running above that, it's probably full duplex. So what's full duplex? Can you make both directions, right? Half duplex. Always runs two-way communication between 2 devices. Half duplex for communication in one direction at a time in a network of up to 255 devices. Now this is for DFI, so this is things. So hopefully you understand. We have to have a need, and I understand that. We need to be able to connect our computer to the device. So we're going to have to connect it through some standardized communication channel, right? You understand that? And then also there's a need to connect the PLC to other PLCs. Most of these, because if you're running an automated system, then a lot of times these PLCs have got to talk to each other. Like if you're running, most manufacturing lines are set up in different modules, and each module has a certain task. And this module can't feed that module unless that module over here tells this PLC that it's what? That it's ready. So there's communication to that. Also, if you're using Ethernet, you can literally program these things and change these PLCs from off-site. If you get permission to do that. So that's what's really neat by using these Ethernet. This is the standard we use all over the place now for wired networks. And it's also the standard for Wi-Fi, believe it or not. It uses the same technology, but instead of using wires, it does what? Yeah. How many devices can be on an Ethernet subnet at any one time? Profibus is a bus topology. A topology is a term we use for networks, the way we connect networks together. So a bus topology would be, you come over here and you take a cable, and then we have 2. We have what we call a down drop, where we have one main cable that runs the entire network. And then we come up and install these T's, and then we'll come in, and then this is where your PLCs or your nodes are. Or they can do what we call a daisy chain. A daisy chain would mean you would have one main cable that would come in, and then you'll have 2 connectors on every PLC, and then you'd bounce them back over. But this is what we call a bus topology, which means you only have one media basically that all of the devices connect to. Ethernet is what we call a star topology. The Ethernet that you know, this could be Ethernet too, but the Ethernet that we know now is what we call the star topology, where we have a device like a network switch or a router. I know y'all heard of routers, right? And then we come in and we make connections to a common spot like this, and that's what we call a star topology, which is mainly what we run to. And so y'all have wireless in your house, and you have a router up there, and then you can plug a computer directly into it, right? If you want high speed, if you want low speed, you use your wireless. So I don't like wireless. So if I go home and I'm working, I use hardwired. I mean, it's great and it's flexible, but and I don't like these little screens. My computer's got a screen on it like that. So I ask you a question, okay? And that's it. So our network, like the BIOSnet, is a bus topology. So that's just the way that you daisy chain that. You took that. I thought you took that 208. You did take the 208 class. Yeah. I thought we talked about the Terminator and stuff on the bus. What do they use down at Roosevelt? Profinet, yeah. So they got switches and stuff out there. I think we got a switch on that seating. Allows for communication with devices that use ASCII protocol, serial printers, bar printers, and that's not normally what we do. We use ASCII to send text information to an HMI display now. So we still use text a lot, and mostly it's just basically ASCII. Over here we use basic ASCII because what else do we need, right? If we're going to send text, because we all speak English over here, right? You understand? You know. So yeah, ASCII's used a lot, and y'all know ASCII now, right? Or y'all know what it is. Serial communication is by far the most widely used. Inside the processor, inside the PLC, most of your communication is parallel. Now, the advantage of parallel is really high speed, right? But I'm not dealing with high speed, right? We're dealing with things that, compared to a computer, you might see these cans flying by. To us, they look like a blur, but to a computer, it's basically, years. I don't know if y'all saw the movie. It was one of the Star Treks where Data got his face burnt up, and y'all remember that one? And he said, "How long was you thinking about that?" And he said, "A millisecond." He said, "Well, that's not a short time." He said, "It's a long time to an Android, right?" And that's what we're talking about, a computer. So you see these cans flying by, but it's still in a millisecond world, and your processor's in a nanosecond world. So your processor's over there running, thousands of times faster. So the advantage of serial over parallel is a lot cheaper, right? And there's no need to have parallel, right? There's no need for me to have a 16-lane freeway if only 10 cars drive on it every day, right? Y'all understand? Or everybody's going 5 miles an hour anyway, right? Y'all understand that? So the advantage of parallel is a lot it's a lot faster, but it's a lot more expensive. And why have a parallel interface on stuff that's running out here in milliseconds, right? When the computer's in a nanosecond world. So the predominant interface so why would I use parallel for this mouse or for this keyboard? How many of y'all can type 1 billion words a second? Not me. I'm pretty fast, but I can't do 1 billion words a second. How fast can you move your mouse? So why would I use a parallel interface to run these guys right here? Right? You understand? So that USB, what does the S stand for? Serial. That's a serial bus. In fact, now we're even using serial ATA. That's our main interface for hard drives and mass storage devices now. Even though parallel would be faster, it's no need to be faster. The F4 Phantom, I don't know if y'all knew that thing could fly Mach 2. It could actually fly faster they never run those engines at 100% because the airframe couldn't handle it. So that'd be like me going out buying a car that puts 500 horsepower out, right? You understand? And putting it in a Volkswagen. First time you let it turn on, it loose, your car would come apart. So we use a lot of serial, especially serial communication between data. So all your Ethernet serial, Wi-Fi is serial, right? You understand that. Profibus is serial, DeviceNet is serial. So just about all these industry standard interfaces that we can connect devices to, these are all serial interfaces because they're dealing with a mechanical world, right? You understand that. We usually don't see this, especially on USB, but you notice when I came back and figured that port, one of the things it talked about was the baud rate. So that's the speed of our transmission, and it's kind of weird, guys. When we first got into the field, if you said 9600 baud, it was basically 9600 bits per second. But that's not true anymore. It's just like I can send gigabit Ethernet over a wire that's only rated at 100 megahertz or 100 megabits. Well, how do we do that? Well, what we do is we have a baud, we call it a carrier, and then we put multiple bits on top of the carrier. So something running at 9600 baud might be carrying 186,000 bits per second, right? You understand? Thank goodness. So the baud rate is really doesn't really tell you how fast your communication is, but for this PLC, that's what it is. It's 9600 bits per second. The problem we have is that the serial interface on that only runs 1200 baud. And the problem we have, you notice what on this one, when I hit that button right there, that little thing turned green instantly. You get one of those, you hit that little button, your PLC responds instantly, but the little thing turns green after about half a second, so because it's only 1200 baud. Ethernet depends on what most of your PLCs that run Ethernet now is 100 megabit. I don't know of any Ethernet that runs over 100 megabit. Does any of y'all know that? It's 10 on a lot of your older ones. Oops, going the wrong way. So what we do is, I know y'all all heard of bandwidth. What's bandwidth? Nobody knows it. Huh?
How much data can be transferred at one time?
Yeah. Well, it's actually the range of frequency that you are assigned. Broadband, so Ethernet is what we call baseband. Baseband means we put one device on the network at any one time, and they get the whole bandwidth of the media. Broadband means we come up here and we divide the bandwidth of the media up into little modules. So I know y'all probably have never heard of baseband, right? Y'all have. So baseband, how many devices can be on the network at a time? One. Now we subdivide them into what we call little subnets. So it's kind of misleading. So it's how much can be on your subnet at any time. And it's actually one device, and a switch kind of takes care of that. Broadband, you can have multiple devices on the bandwidth, but you only get a little section of the total bandwidth. Does that make sense? Okay. So what they do is on a network is that when you only get control of the network for a real short period of time. So what they do is they take your information and split it up into what we call packets. And then you send a packet out. And then you come off, and then somebody else can do what? Send a packet. And this is really comes into play on a baseband network like Ethernet, because you can't have somebody transferring 1 billion bytes of information and have control of the network the whole time. So what will they do? They send a packet and then they release the network, right? You understand? So that's what they're talking about, framing. So when you download files, you're not downloading the file, you're downloading a bunch of what? Packets. And if you ever run a trace on your circuit, the way the Ethernet is set up is that sometimes a packet might take a different route one way than it takes the other way. It's really, really neat. If you ever run a trace on how your packets flow through all these switches and everything out there, our routers. So framing is taking the information and putting it inside what we call a frame, right? You understand? And then we transfer that frame. And then usually we release the network because Profibus is baseband, Ethernet is baseband, right? You understand? So it just sends these packets. The size of the packets depends on what protocol you're using. So that's framing. And baud rate, framing. This is basically a frame, and this is a serial frame. Frames are a lot different now than what they used to be. So typical frames now consist of what we call a header, and then it consists of the data, and then it consists of a trailer. The trailer is usually error correcting codes that they put in there to figure out if the data was received right. And then the header says, this is who I am, this is who I want to go to, and it's got synchronizing data inside there. And then of course this would be the data. So we don't use stop bits and start bits, and we don't use parity much anymore. This is the ORS-232 interface, which is what I'm using to communicate with this. So where's my RF links at? Did I close it out? Here we go. So this is the speed. What's our speed? 9600. Parity. None. Then it says I'm using one stop. So the way RS-232 works is it sets at one level, and then it drops to what we call a start bit, and then it sends the data, and then when it gets through, it always brings it back to where the start bit was. Now, is this important? Yes or no? No. It's not important. Well, I don't know why the book even brings this up. Does Rich understand how it works? Yes. Do you need to understand how it works? No. But you do have to have an idea of the difference between baseband and broadband, because when we get in here, most people, all y'all have heard of is what? Broadband. So they take your information and they put it on a carrier. We call it modulation. Right? You understand? And that modulation carries a lot of data. You get that little data frame, put that sucker out there to a mod. And then when you come back, when you receive it, you have to have a device that strips that data off. And that's called demodulation. And what do we call those devices that modulates the data and demodulates the data? Modem. They got a modem in their house. So that's what you're doing. That's what allows you to be, that's what allows us to do broadband. So what you do is you have a certain, what we call carrier. You have a certain baud, right? And then you place all your data on that carrier. And then you zip that sucker out there, and then everybody else can be on there at the same time. But once we get into my network, we're using baseband. In baseband, that's where we got to deal with the frames. We got to deal with half duplex and not full duplex, and you got to understand that. We're okay. So baseband, on your network, how many devices at a time? One. And what keeps them from tying up the network? They do a frame, and then they release the network. And these guys out there saying, they're listening to the network, and they're saying, oh, it's free. Ethernet works a lot like the old party line. Y'all remember the Beverly? When we first got our phone, it was a party. They had no private lines out there, which means you shared your number with what? Quite a few people. And before you made a call, what did we have to do? No, we picked it up and listened. And if there was somebody on there, we were supposed to do what? Listen, yeah. We were supposed to hang up. And then I'd come back after a little while and I'd do what? I'd listen. And if nobody was on there, what would I do? I'd dial my number. And then everybody else who was on our party line, that's what they was, and that's the Ethernet, guys. That's what Ethernet does. So I release my packet. I listen to the network. If there's nobody on there, I'll send a what? Another packet. If there's nobody on there, I'll send another packet. Somebody said somebody's doing the same thing. They said, oh, it's free. They send a packet, right? You understand? And they keep releasing networks, and that's the way baseband works. So if you ever watched the Beverly Hillbillies, that was really good. That's when they had party lines, but they lived way up on the Appalachian Mountains, and all they had was party lines. So when they came into Beverly Hills, they made them put a party line in, so Granny could listen to everybody on the line. So you can do that when you're a millionaire. Parity bit, parity check. This is not really important for us. We do need to understand this, and this determines what type of cable we have, especially when it comes to Ethernet. So a DTE, these are guys that initiate communication, and that's who we're communicating with. So this PLC would be a DTE. This computer would be a DTE. It's called data terminal equipment. A printer would be a DTE, right? You understand? So anything I'm communicating with, or anything that's developing the transmission, is a DTE. A DCE is what the information flows through to get from DTE to DTE. So a router would be a DCE, right? A switch would be a DCE. A gateway would be a DCE, right? Y'all understand that? So all those would be DCEs. Now, what this depends on what type of cable that you have to get to connect these suckers together. So if this was to connect a DTE to a DCE, if I can show this, and I'll pass this around. Okay, where's my camera? You'll see this color code right here. But you can see this, on the left, I've got orange, right? Orange, white, orange, green, white, blue, blue, white, green, brown, white, brown. Now, if I was going to connect to a DCE, the other end of the cable would be exactly that same color code. So can you see this? Oops. I'm going to bring this up, and what do you see? Okay, so this cable is designed to connect a what? A DTE to a DTE.
Alexa, I'll pass it.
So when I look at this one, hopefully you can see orange is on the left, right? Huh? I'm gonna pass it around. When I put this one up, green's on the left. This is what we call a crossover cable. This is designed to connect a DTE to a DTE. So if I'm going to connect this computer to that PLC, if I use that other cable, it won't work. If I use this cable, it will. If I hook this to a switch, then I would use straight through cables. Or if I hook it to a router, I'd hook a straight through cable. But if I hook two computers together, I need to use a crossover cable. Huh? Yeah, it flip-flops the greens and the oranges. If you look. Yeah, there is. We call it the 586, the IEEE 586A and the 586B. The B is orange, white, orange, green, white, blue, blue, white, green, brown, white, brown. That's the B, and that's the standard that we use on both sides for a straight through cable. You could do two A's, but that's not the standard. No, a DCE to a DCE is a straight through cable. A DTE to a DCE is a straight through cable. The only time you got to use a crossover cable is when you go from a DTE to a DTE. That makes sense? So if I'm going to hook this computer up to that PLC or that PLC, then I got to use a crossover. Yeah. You swap the orange and green, but you can look up the 586, the 586A, and the 586B. You can buy crossover cables that's already made, but the problem is you're to the lengths that they make, right? You understand? So we got everything over here. We make all our cables. And they're not hard to make once you run them. Huh? Yeah, I use a crimper and cut them and put them in the right color code. Get it. You got to be careful with the twist. So these are all homemade cables. That's a crossover cable. And then this right here is a straight through cable. So DTEs, these are data communication equipment. And what are the DTEs? These are the guys that initiate the information and receive it, right? So these are the guys that, and then DCEs is what it flows through to get between those two. So what would your modem be? DCE. A router. DCE. Your printer. A DTE, right? An HMI panel. A DTE, yeah, what do you mean? Is everybody okay? Y'all need a break? I didn't see anybody do this. Y'all need a break? Okay, let's take 10-minute break, guys. Got one more chapter we got to get through before we actually get to lab.
Did you already take roll?
Yes, a long time ago.
Okay, I wasn't
I know you were. So let me bring the roll back up.
here. I did get finished enrolling.
Oh, you did?
Yeah.
So your financial aid came through?
That's why I was late.
We're teaching a class called Cable Splicing and Installation, by the way. We all learn how to make those things. What's your last name?
Sure.
There we go. All right.
Thank you, sir.
Did Mr. Elias come in? Need to let me know you're here, right?
Right.
See the row right there? It's got A up there. Huh? They should already be up there. Huh?
Some chapter.
Really?
Some percent.
Hey, it might be the ones Nancy used. If I need to go back and check that, I'll do that. In fact, the next chapter I've added some stuff to it. I need to update those. I have a tendency to do that. So I'll refresh them because some of y'all don't have books, and I think we got a test schedule for Wednesday. Huh?
Come back.
Huh? Yeah.
Come back up.
Yep. So y'all have a lot of time to study for it. So I'll put a review up there as soon as I can. This is not one of the main classes that I teach, but it looks like I'm gonna have to teach it from now on. So this is probably maybe the third time I've taught this. Maybe four.
What's the one with each?
I teach everything. I teach a lot. I normally teach that advanced class. So I do the advanced PLCs, and I do the we call it PLC3. It's PLCs and systems, and then I do the troubleshooting, the AU, T208 class. I do solid state. I usually do digital. We're trying to turn that over to somebody else. So I do cable splicing, I do digital, I do solid state, I do fluid power every once in a while. But I teach a lot of things.
IC.
Hmm?
IC. Back out.
What's that? Instrument control? No. I worked on computers. I was a field engineer for a while on computers. I worked on scales, the digital scales. I worked on SCR drives. I worked on, so I don't have a set background. I'm a jack of all trades. Yeah, we got another lab job we want y'all to do too. That's going to cover this chapter because this is on test. What we're doing tonight, this is there's stuff on this on test.
I'll just
Number systems. No, we'll do that. We'll do that in here. This is that's numbering systems. No, this is still the same thing. Where's the other one? No, these right here are going to be in class labs. Because it's asking about specifics on the PLC. Yes. How do you address input ports available? No, these are going to have to be in class. We'll have to do these on the PLC. So the only one that's actually going to be do would be the memory system. No, let's see what chapters have we done. We did number 7, 3. We did 1.
One AC.
Yeah, one of them's electrical.
That's
I should have let you teach it.
not that. I could follow the
Yeah, I'm still trying to get the flow of the class. And it takes you a little while when you teach class to get the flow. Yeah, we're missing Monday, but we still get the same number of days. So mini term we get 15 classes. And then we have a final, but they schedule the finals on Friday for mini term classes. So we lose that class because we give the final to 15 classes. So it's hard to get people to come back out on Friday. And then plus, they're having y'all know we're having 2 graduations now. So we're having we used to have 1 graduation every year. We'd have it in the end of the spring semester. But now we're going to graduate at the end of the fall semester, at the end of the spring semester. So we're going to have 2 graduations every year. And we're not going to do it at the Birmingham Civic Center anymore. We're going to do it in the auditorium over at the Birmingham, or the gym. That place is huge. It's nice. Huh? What? With an application running on the computer. So this is what we do now. We don't use ribbon cables. RS-232. So the 1100, the 1000, and the SLC 504 both use the data highway. The RS. It's not RS. It's EIA now, but it's 485. No, it's TIA 485. EIA is the one that went out of business. Also, what we usually have to be, and y'all are not going to do this, but we also have the ability to password protect your PLC. So basically, anybody that's running that has anybody that's got the application on their computer, they could literally connect to a PLC and make a lot of changes to it. So odds are, if you got out in the industry, they're going to password protect the PLC. On off, let's see, disable, turns all the PLC outputs on. Offline, so if we're gonna write the program, then we need to put the PLC in the offline mode, right? Everybody okay? On this one, we got a key on the front. I need to steal this key out of here. We got a setting that says program. That's offline. So this is where you can actually program the PLC. The center switch is remote, which means you can switch it between run and offline from your application. And then you got run on. Okay? What gets people, you say what's the three positions, somebody say program, that's not really the program, it's actually offline. Right? Understand that? We like to leave it on remote. And that way you don't have to worry about the switch. Because what happens, you try to download it, it's in program. In run, and then it tells you, you gotta switch it to run, you gotta reach up there and flip the switch, right? You understand? If you have it in remote, then what can you do? You do it from your software. It'll automatically switch you from remote, when you download it, if it's in run, it'll switch it to off. Switch it to offline, then it'll come back and go online, and then it'll switch to run for you. So what's nice about having the key is I can put this thing in run, and then what can I do now? I take the key out, and then nobody can change that code unless they have the one. Guess what? That key works in every one of these. So this one key would work on all of them. So all you'd have, if you had a key, I could take my key out, but if you had a key. So the run mode, when we switch it to the run mode, then the PLC is actually told to run the program, right? Understand that? Everybody okay? Now what Allen Bradley does, when you switch it to the run mode, if you got your computer hooked up, it'll actually display what we call a monitor that shows you what's going on. This is one of the differences between the Siemens PLC. Once you switch it to the run mode, you have to tell your application to switch the monitor. So it's got a little sight glass thing up there. I'll try to demonstrate some of those just to know the difference. And guys, what you're going to find out, that everything that we've talked about so far applies to every PLC that I ever had my hands on. So even though you might not get the Allen Bradley or the Siemens PLCs, if you learn this real well, you'll be able to do what? You'll be able to pick up any PLC on how to program. All you got to do is figure out, how they do that. It's just like over in the robotics lab, we have 4 robots we learn. All of them are different. But once you learn one, you can do what? Learn the rest of them. Are we okay here? Any questions? Online monitor, that's what we're talking about. Siemens, when you switch it to online, when you upload it and ask you want to go online, what it'll automatically do is go into the monitor mode. Siemens PLCs, their application, you have to tell it to monitor. Force. What do you think Force allows us to do? It allows you to override, so let's see if we got our application up here. It allows you to override an input, or you can override an output. I still have it connected. Yeah. So I'm going to come down here. So down here at the bottom, we got what we call a, you see force? All right. So I'm going to force an output. And I'm going to put this up right here. So right here, this is under control right here, right? See that? And I'm going to come over here to the next output. And I'm going to put a 1 there, and I'm going to hit enter. What did it do? Is a program doing that? No. I could come over here to the one that's turned on, and I can put a 0 there, and it turned off. So even though the program's still running, I have the ability to force these. Now you got to be careful with these guys. We had a guy at U.S. Steel was working in number 8 blast furnace up in the hopper where they dump the stuff in there. And number 8 blast furnace ran a pressurized system, so they had 2 doors. So a material would come in on the top, they'd close the top door, and they'd open the bottom door. The guy got in there working. He locked out everything he was working on up there, and he went down there and told somebody to force that thing, and he forced the wrong door, and they didn't have that one locked up, and he cut it in 2. So be careful when you force. You need to understand what's happening. We was out. We had a line and that had it was a galvanizing line, and they had a strip welder where you could weld the strips together, and they had clamps that would come down, and that line would run like 700 lines a minute. It'd be screaming. And we was in there playing around, and I was forcing an output, and those side clamps were coming down. But the problem is that luckily they was running a narrow strip, and the clamps missed. But if I'd have stopped that thing when it was running 700 feet a minute, it would have crammed that thing up. So be careful and understand when you force these things. So to get this back up, what I'll do is I'll come up here and just delete that. Yeah, it'll leave it on. What you have to do is you have to come up to the force table on this thing, and you just delete what you had there, and then you entered it, and notice it went back to a dot. Oh yeah. No, it said I couldn't do that. Yeah, I did. So it would, but what that would do is what? It would take all your forces off, right? Makes sense. If we can force outputs, what can we do? Yeah, we can force inputs. So I could change the state of that input. So this is called forcing, but you got to understand when you force one of these inputs or one of these outputs, the consequences, or you got to know what's going to happen when you force it, right? Does that make sense? And what this basically gives us the ability to do is troubleshoot. So I've got a system that's not working, and I want to say, well, is this what's causing it not to work, right? You understand? And I can force it, and then if it works, right, then we got no problem. I mean, but you got to understand, right? When you force these things, you need to understand the consequences of what you do. Everybody okay? Every PLC that I've ever seen has the ability to force it. Relays usually have a button on top that you can press, where you can force a relay. So you can force relays, but you got to be careful. Caution, using the force mode with extreme caution. An operator can start a motor using the force instruction. The action has a potential of causing bodily harm to the assembly line worker, right? You understand that? So, that's that chapter. Any questions? So we're going to start into the next chapter. I'm not going to let y'all go early. I'll say, but what we're going to do next class is start next class before we take the test. So what we like to do, we got 2 options, and it can be your choice, but usually everybody chooses the same thing. We can give the test at the start of the class, where we can't let you go. Every class counts as 2 classes, so you can't leave when you finish the test, right? You understand that? So what you would have to do, if you got through early, what would you have to do? Get out of the way. Or we can give it at the end of the class. If we give it at the end of the class, then if you get through early, you do what? You can let it. So which one do you want to do? The end? That's what you what we try to not do is we might have to do a little bit, but what we're going to do is we're going to do 2 classes. And these are basically hands-on labs. Well, we'll try to go down to the lab and we'll introduce you those. And you're going to go, by the way, we're going to work in groups. We're going to work in groups too. Okay. We could choose numbers, let you do it that way, or you can choose your own partner. So, huh? I don't think we got it on there. Some people's left. Really? Oh, look, so somebody might have to work about that. We should have enough PLCs down there, especially since we're adopting some of the 1100s over that. And, what we also want to do is to go over to, let's just plan on doing that first. Let's plan on meeting in the mechatronics lab. Y'all know where that's at? Y'all know the college has 2 gates. Okay, y'all know the south gate. Not the one with the red light, the next gate. You come in that gate, and the mechatronics building is the one right on the right. And it's got an outside door. You don't have to drive around and park. We got an outside door to the parking lot. We actually have 2 doors. The one on the left's got robotics on it. If you come in that door, we have a hole in the wall you can go through. But the mechatronics lab is actually the next front. And what we want to show y'all is some PLCs in action. What we're going to do is, first of all, is we're going to let you try to run the line manually. So you don't. No, it's the Hall building. Yeah, the south gate, the next gate down, not the one with the red light, the next gate down. As soon as you come in that gate, park. It is the building on the left. It's actually building H.
That's cool. I know the state.
Yeah, well, my office is there. Right. Some of them are. But you can't miss it. It's the next. We've only got 2 gates into the campus. One of them has a red light. One of them don't. When you turn into the one that don't, which is the south gate, the one that's closest to the Bessemer Civic Center, park. The Hall building is the first building on the left. It's the one that's got the glass roof. I'm under the glass roof. Don't go around the building. Park in the lower lot. We have 2 outside doors. The mechatronics lab is the robotics lab is the one that's got robotics in the window. There's a tree out there that's got robotics in the window. The mechatronics door is the next one to the right, but it don't make any difference. I'll have both of them unlocked. If you come in the robotics lab, there's a hole in the wall. It's got doors. And you come into the mechatronics lab. We'll look at the Amatro line, which runs Siemens 314 PLCs, and then we'll look at the Festo line, which runs the Allen Bradley 1500s, except for one station. And we have an HMI panel over there. You can see that. And you can also see where in PLC 3 what we do is we actually adopt that line from Allen Bradley over to Siemens PLC. So one of the stations still has a Siemens PLC. So and what we're going to do is we're going to disconnect the PLC, and we're going to hook a module up there where you can look at the sensors and you can control the outputs. And what we're going to try to do is manually run the line. So you can see what a PLC does. You're going to see what a PLC does, but you're going to do it manually so you can understand when we deal with these inputs and these outputs exactly what's going on. Are we okay? So that's going to be what we're going to do. Then we'll come back over here. We'll go to lab 200, and then we're going to figure out who's going to assign the PLC, and then you're going to figure out what your PLC is, what it does, how many inputs it has, how many outputs it has, whether it's syncing, whether it's sourcing, whether it's relay, and all that kind of stuff. We'll figure out that too. How many inputs does it have? How many outputs does it have? Any questions?
When were you talking about?
The test is going to be at the end of class. Only if you want to come in on Labor Day.
You can come in, but odds are the gates are gonna be locked and I won't be here. But if you wanna come in and sit out there, no, it's gonna be Wednesday. Y'all know Monday's a holiday, right? So the test is gonna be Wednesday. That 1, 2, 3. And then electrical, basic electrical, right? Huh?
Oh, three was the last chapter.
Yeah, we did number systems and then come back and pick it. This is chapter 2 we did tonight, right?
Or is it number, is it chapter 1 in that book?
I think the chapters are still the same, right? Yeah. Okay, y'all pass these out. The guy that wrote the book has got some problems. So we're going to make a few corrections. And then hopefully we can get to this tonight too, because this is pretty important. And then what's going to happen, as soon as we get through with chapter 6, then the lectures are going to slow down. And then we're going to be in what most of the time? Identify the electrical symbols for various switches, describe the operation, and proximity of Hall effect or some. No, let's don't do this again. We'll come back and pick that up. This is the one I want, chapter 5. So right now we're going to skip over chapter 4. So we can start programming for them. Then we'll come back and pick that chapter up. So one of the things you gotta learn, guys, and I'll try to fit it up in the handout section. Let me start another